Good morning, Astronomy 1010. Welcome to our 9th lecture. I believe today we're going to finish up some little bits on the sun, and we're going to start a chapter on the overview of the solar system, which is chapter 7 in our textbooks. That's going to address some basic issues about planets, making sure you know their names and some of the facts about them before we delve into the more specific topic of terrestrial planetary geology, planetary atmospheres, and eventually learning about the Jovian planets and beyond. So the first order of business is to figure out what little bits of the sun that I could still teach you that might be helpful going forward. I don't believe we got into the nitty-gritty of nuclear fusion inside the core of the sun. I think I told you the overall reaction, but I don't think I actually did it proper justice. Is that correct, Jenna? All right. Another thing that I'd like to do today is just take a moment to identify what our lab is going to be. I think it's the rotation of the sun. So today we're doing lab 8. Let's just make sure everything's properly numbered because things got a little bit goofy. Yeah, lab 8 is on the rotation of the sun. To do this lab properly, it's going to be helpful to have a piece of tracing paper. That might not be easy for everyone to come by. The pages that you're really going to need are the ones on the sunspots and then the 2 worksheets. So 13.6, 13.5, and 13.4. And if I hit print, I think I've already got some of this printed out, but I'm going to hit print again. I'm going to do pages 4 through 6. You guys might want to think about doing the same if you have printers. 4 through 6. Let's see if that works out. I believe I have tracing paper kicking around somewhere, but I might have to tear my place apart a bit to find it. I'll do that during the tea break. If you don't have tracing paper, you might use a piece of wax paper for cooking, or even just a regular piece of printer paper. You can sometimes see through them if you use enough light. We're going to want to try to make a model of the sun and track some sunspots across to measure its rotation. So in our last class, we learned that there were rules for magnetic fields, and these rules for magnetic fields were part of the reason why the sun looks so gnarly. Where's my darned slideshow here? The reason why the sun looks so insane at X-ray wavelengths is because X-ray wavelengths can track the magnetic activity on the sun through a type of radiation called Bremsstrahlung radiation. This is sort of an advanced topic in physics. It's where free plasma particles strike magnetic field lines and eject X-rays into space. And all of this magnetic activity is related to the sun's 11-year solar magnetic cycle. I've referenced it before. We talked about this in our homeworks. Hello, Ryan. I thought I'd just say a couple of quick words about it before we moved on to nuclear fusion. So today's lesson's on sunspots. Let's just take a couple of quick lecture notes on that so you know a little bit about them. So we're going to talk about sunspots and the 11-year, let me spell it out, solar magnetic cycle. Kind of a big topic in solar system research. Sorry, my printer was spitting out lab papers onto the floor, so I had to catch them. So sunspots, if I haven't taken any notes on them yet, sunspots are maybe Earth-sized regions of cooler plasma and probably a bit of gas mixed in there too, that are trapped by magnetic field lines They're trapped by magnetic field lines at the sun's photosphere, which you guys will remember is kind of like the equivalent of the surface of the sun. It's the surface in terms of the light, the visible light that it gives out. And that means that where these magnetic field lines terminate, we would expect to find sunspots there and there. Let me give you two different sort of views of this thing here. Let's try to go to 34. Let's just jump ahead a little bit. Here's a picture of a sunspot in relationship to the granulation that I talked about last time. You guys remember what the granules are, right, Kim? Right, Jenna? What are the granules? Tell me something. Illuminate me.
They are Texas-sized blobs of hot and cool gas, and that delivers the light to the surface of the sun.
Excellent. Just what I wanted to hear. And although they have slightly hotter and cooler temperatures, the temperature of a sunspot is much cooler, like maybe 1,000 Kelvin or more cooler than the surrounding photosphere. And using the Stefan-Boltzmann law and Wien's law, this tends to make them a bit darker and redder than the surrounding materials. Usually we find sunspots at the base of magnetic fields, and there's a test that we can do involving the splitting of absorption lines that conclusively proves that these sunspots are being trapped by magnetic field lines. Because magnetic field lines come in a loop, there's usually a pair of sunspots that are kind of bound together by that magnetic field line loop. And they're caused by the fact that the sun is undergoing a differential rotation and twisting up these magnetic field lines. So let's say some more things about these sunspots. The sunspots are regions of cooler plasma trapped by magnetic field lines. They usually come in a north and south pair. And they also come and go with an 11-year cycle. This is how we learned about the sun's solar magnetic cycle before we had potent X-ray telescopes that could image the outer layers of the sun. We knew about it because we observed sunspots coming and going with a pretty regular periodicity, a period of 5.5 years of lots of spots and then 5.5 years of almost no spots. For those interested, we're currently right now in a solar magnetic minimum, so it's quite rare to see sunspots these days. So you get 5.5 years on and then 5.5 years off. And this is the subject of a lot of solar, sun research. It's one of the reasons we've been imaging the sun using the Solar Dynamics Observatory, because people only have a vague idea of how this works. It's part of a very complex subject in plasma physics called magnetohydrodynamics. What happens when you have gas, plasma, and magnetic fields all mixing around together? The results can be really weird and unpredictable. Let me show you a graph, and there's some interesting story to this. Do you remember who the first person to study the sunspots was?
Was it Galileo?
Yeah, he eventually went blind by staring directly at the sunspots with his telescope. You're going to do something similar, a very classic astronomy lab today, where you basically track some spots rotating around the sun and then do a simple calculation so that you can calculate the rotation rate of the sun. So sunspots, just at their first blush, are useful to us in that it shows us something moving across the sun that lets us calculate the sun's rotation. That's a kind of iconic astrolab that you'll do today. There's a graph here showing you a plot of sunspot activity since the observations of Galileo in the mid-1600s all the way to the year 2000 or so. And you'll notice that for most of the time period, there's this perfect cyclical variation of 5.5 years of lots of spots, 5.5 years of no spots. The number of spots seems to change, but the cycle, the periodicity itself is pretty uniform, with the exception of this one creepy time period from the year 1650 to 1700, all sunspot activity on the sun stopped. And today, no one knows why this happened. It's this time period that we refer to as the Maunder minimum. If you're interested, you could read about it on Wikipedia. They did notice changes in global temperatures on Earth happening around the same time. What the connection is between the sunspots and a mini sort of climate change on Earth is not known. But people are very interested in this break in the magnetic field activity of the sun and what might have caused it. One thing to keep in mind is that from the year 1600 to the year 2000 is still only a period of about 400 years. That might seem like a long time to you, but it's a very short time for a star. Stars evolve over hundreds of millions and even billions of years. So there could be other more complex cycles that don't reveal themselves until 1,000 years or 10,000 years. We've only been intelligently looking at the sun for a very narrow window as far as the star itself is concerned. So this seems creepy to us, but it might be that we just haven't been observing the sun long enough to get it. Anyways, these are all some kind of fun facts about sunspots that I thought I'd share since our lab is based on it today. Let's see. Let me check my my time window here. My goal today is to do what I just did, a little bit on sunspots. Oh, I want to do a little calculation showing you how this might appear on the test. And I think this might be helpful for you guys in understanding the nature of a sunspot. So let's bust out our calculators, my two students who are interacting with me today, and let's try a little, sample calculation together. Let's do a sunspot investigation. Let's imagine that we've got a spot somewhere on the sun. And then over here, we have some of that granulation. And this is the good old-fashioned photosphere. Well, it's all the photosphere, but this is the normal photosphere. And this is our spot, okay? You guys might remember that the temperature of the photosphere is typically 5,800 Kelvin. And that's pretty uniform. Because these sunspots are trapped by magnetic fields, they continue to shine away radiation, and they cannot sink back down into the convection zone where they would be reheated again. The result is that this giant Earth-sized region just keeps shining away its light and getting progressively colder. Eventually, it could reach a temperature as low as, I don't know, 4,000 Kelvin. The goal is to answer two questions. One, how much less light is the spot emitting? Question two, what's its peak wavelength of emission? Now, I can tell you, but I think it would be pretty cool if you guys could remember what formulas would be best applied here to answer these two questions. Anyone know what formula tells you the quantity of light emitted based on its temperature? No?
Is it Wien's?
Wien's law is going to be the answer to number two. So this one, we're going to want to use Wien's law. The answer to question number one is best used for the Stefan-Boltzmann law. The Stefan-Boltzmann law is the one that tells us that the brightness, remember the brightness is the amount of light emitted per square meter on the sunspot, is the Stefan-Boltzmann constant times the fourth power of temperature. All right. I happen to have the Stefan-Boltzmann constant memorized for you. It's 6 × 10⁻⁸ watts per square meter per Kelvin to the fourth, multiplied by, let's do the sunspot first, 4,000 Kelvin. Why don't you guys punch that up for me?
I got 15 billion. Oh,
That's perfect. Hold on one sec. I'll write, just give me one sec, guys. So sorry about that, Jenna. Did you say 15 million?
yep, million.
All right, that sounds about right. What are the units?
It'll be watts per meter squared.
Right. Now, we'd like to compare. So even though a sunspot is black, there's still a significant quantity of light coming out of it, right? If we'd like to know how much less light, Jenna, what we could do is we could, rather than calculate this for the regular photosphere, we could use a proportionality argument, and we could just take the ratio of their temperatures to the fourth power. In other words, the brightness of the normal photosphere as a ratio of the brightness to a spot. If I were to divide this twice, the Stefan-Boltzmann constant would be the same and cancel out in both cases. And I'd end up getting the temperature of the photosphere over the temperature of the spot raised to the fourth power. Now, I just did a little algebra trickery in there, but I suspect that no one really cares. If you're interested, I can explain that. Let's take the ratio of the temperatures, 5,800 Kelvin to 4,000 Kelvin, and then raise it to the power of 4. Can you guys do that for me? Kim, you remember how to take your fourth root as well, correct?
Say that again.
You know how to do the fourth power, right? I said fourth root. I meant to say fourth power.
Yeah, I was like, what? I was like in the middle.
All right, I should just leave you alone then, clearly. Yep.
I got 4.4.
Okay. So about 4 times, right?
Yes, yeah. 4.5 maybe.
4 times more light from the photosphere. Or 4 times less light from the spot. I'm going to answer question 2 up here, but I'm going to have to erase a little bit. Hopefully that doesn't bother the people that are participating here. Let's do lambda max equals 3 million nanometer kelvins divided by the temperature. Let's do it twice. Let's do it once for the photosphere, and let's do it once for the sunspot. So for the photosphere, what would you guys calculate? And for the spot, what would you calculate? I'm not going to bother writing it out. I'm just going to have you guys plug in the temperature twice and tell me what the answer is. 2 sig figs will suffice. Let's do it.
Okay. For photosphere, I got 520
Yep.
nanometers.
Yep.
Okay. And I'm going to do the light now.
The spot, you mean?
I got 750 nanometers.
Okay, and you know what regime of the electromagnetic spectrum these two wavelengths are in, correct? Are we good enough at our electromagnetic spectrum that you know this now?
Yes, I know the photosphere is in the visible light, but is the sunspot past that?
It's right on the edge.
Okay.
I opened up, I figured we might use this at some point today. Here's, let's look at the visible spectrum real quick on slide 19, function F5, 19. Notice 520 is right in the heart of the green, but actually, Jenna, 750 is right on the edge of what the human eye can detect as red. The eye is starting to taper off and not work as good there. So 750 is the boundary between red and infrared, okay? This is visible green, and this is on the edge of red/infrared. All right, now that you've learned all this stuff, students, it's time for the million-dollar question. And this is a question that astro teachers love to ask their students. Suppose the sun were covered in one big giant sunspot. What would it look like? Suppose the whole surface of the sun were covered in a big sunspot.
It would be significantly darker.
That is true, but what would it look like to your eyes?
Would it still be pretty bright since we just figured out that sunspots emit a lot of light?
Yeah. Yeah, the sun would still be bright if it was covered in a sunspot. What do you think it would look like color-wise?
Sorry. Red, like a dark red.
It wouldn't look dark red. It would probably look a bit darker. But Jenna, remember that the color, the so-called color temperature, the temperature based on the color based on the temperature, is still quite similar to an incandescent light bulb or a garage light bulb. From outer space, the sun would probably look pretty white still. It would honestly probably look similar, but maybe a little bit from the ground, it would certainly look a little bit more orangey reddish. I don't think it would be a dark red, but it would look significantly redder. But for the most part, although yes, it would be dimmer, and although yes, it would be a little bit more orangey, it still actually might look the same. If you think about what an incandescent light bulb looks like, the filaments there is at a temperature of 4,000 Kelvin, but it's still emitting enough light across the visible spectrum where it kind of has a whitish hue, you know? It's not quite as cold green as some of those fluorescent tube lights, which you know have a different sort of feel to them, a different color look, right? The orange incandescent bulbs are a bit rosier and more flattering to the skin, but for the most part, it would still be bright and white and maybe just a little bit more orangey red. Okay, nicely done. Let's change gears. Let's go to the heart of the sun and learn a teensy bit about nuclear fusion. Today's class, unfortunately, is just going to be a bit of a hodgepodge of different topics, but it seemed like the right thing to do. Especially because I might ask you to do this on a test. Wink, wink, nudge, nudge. Okay. So I wanted to train you on that. Can I erase? This next section is going to seem a bit nutty, but I think it's a good idea for us to talk a wee bit about nuclear physics, because we're going to find that nuclear reactions in small scales take place inside planets as well as stars, although not anywhere near the same quantity or the same type. So at the core of the sun, I don't think we did this. The nuclear core of the sun, energy generation proceeds by fusion at a key temperature of 15 million Kelvin. At a temperature of 15 million Kelvin, which we believe to be about the temperature at the center of our star, hydrogen fusion turns on and generates energy. And I'd like to teach you the process by which that reaction takes place. It's something known as the proton-proton chain. But before I get to that, let's just learn a wee bit about nuclear fusion. I've got a picture here. Let me see if I can find it. I'm still recording, right, guys? Let me just, yes, okay. I paused it for a second and I just got paranoid. This cute little picture, 57, tries to explain the difference between fusion and fission in a cartoon form. The two types of nuclear reactions both involve mutating and changing the nucleus of an atom. That means you're converting one chemical element into another chemical element, the way the old alchemists of yore would have liked to have done during their quest to be able to create gold. So in fission, which involves a crack or a splitting of a big nucleus, you take a big fat nucleus like uranium-235, which is kind of inherently unstable because it doesn't have enough neutrons in it, and you agitate it maybe by smacking it in the face with a high-speed neutron. And when you do this, the giant nucleus fissures or cracks in half into two, they're called daughter nuclei. In the case of uranium-235, the daughter nuclei are cesium and rubidium, both of which themselves are radioactive. You also release some extra neutrons, and you release a gob of energy, which is almost always in the form of gamma rays. Remember that gamma rays are a type of light that are very, very short wavelength, but very, very high energy. The trouble with nuclear fission is that nuclear fission leaves behind some dirty waste products, some radioactive materials. Those usually take the form of the spent nuclear rods that have to be removed from the heating element of the power plant and then dumped in some toxic waste disposal site like Yucca Flats, New Mexico. Nuclear fission is a dirty form of energy, at least on the small scale, because of its, nuclear waste is never something people think of as a good thing. Ironically, nuclear fission is actually a cleaner form of energy than burning carbon, because at least you don't put a lot of carbon soot up into the atmosphere, ultimately probably takes the form of CO2, and that actually is quite dangerous for the planet as a whole. But that's a topic for a different time. Today we want to talk about how the sun does nuclear reactions. It uses a process called fusion. Fusion involves gluing two smaller nuclei together into a slightly bigger nuclei. In the case of the sun, we're going to take some hydrogen nuclei and we're going to fuse them into a helium nucleus. This also releases energy, albeit a smaller amount, but the sun overcompensates for this by having a lot of nuclear reactions per second, so the sun can actually generate quite a bit of energy. The beauty of nuclear fusion is that it is a clean form of energy that does not leave behind any radioactive waste, and it's basically free energy that comes at the expense of a couple of small nuclei. It would be really cool if human beings could harness the nuclear fusion in the sun. We would basically get an unlimited source of energy for $0, and that would change the issues of climate change in the Earth, because once it didn't cost people anything and it was environmentally sound, everyone could be in agreement on it. Unfortunately, the reason that we've had trouble as human beings recreating fusion is because you need some kind of a berserk machine that's almost the size and mass of the sun to actually raise the temperature of some plasma to this berserk temperature of 15 million Kelvin. We don't have the technological capabilities to quite bring a large amount of plasma up to this temperature, although we have tried in the past, and there is continuing research on it today. The nice thing to do is to start off by just learning the nuclear reaction cycle by which the sun generates energy. It's known as the proton-proton chain. So the reaction is called the proton-proton chain. I have a lot to say about the nuclear physics reaction, but the trick is going to be to not get so caught up in it. I'd like to see if I can keep this to about 15 minutes or so. That way I can move on to talking about planets a bit today as well. Let me just say goodbye to my house guest, and then I'll get right back to you. Sorry, guys. That was a house guest taking off. So the proton-proton chain here is as a nuclear reaction cycle by which the sun generates energy. And the net reaction, the net result, which is worth thinking about before we get started, is that 4 hydrogens are going to stick together and turn into 1 helium nucleus. And 2 gamma rays. Let me write that a slightly different way. 2 gamma rays. I think I put this on the board last time, but I'm doing it again. And the reaction is going to take place in 3 steps. In the first step, well, so let's just make sure that you guys remember what all this stuff looks like. What is the composition of a hydrogen atom? Let's start there.
Is it 1 proton, 1 neutron?
Nope. That's, well, that is a hydrogen, but that's a hydrogen called deuterium. When we write down hydrogens here, we're mostly going to be talking about protium.
Yes, it's just 1 neutron. Sorry, 1 proton with an electron orbiting it.
Okay. Except keep in mind, Jenna, that by the time you get into the interior of the sun, all of the electrons have been completely removed from the protons. So this is what it might look like if you could go down into the radiation zone or even the core. You'd find free protons floating around with free electrons, the occasional gamma ray, and every now and then the occasional helium nucleus, okay? During the proton-proton chain, the only things that will be involved in the nuclear reactions are the protons themselves, okay? the protons themselves are going to collide. The electrons, they can't really undergo nuclear fusion in the same way, all right? Let's take a look using the whiteboard for just a second and try to imagine what would happen if two protons were to go on a collision course. So I'm going to attempt to do a drawing here, although it may not be very good. So here's a proton, and here's another proton. I can use black and probably put a cross in the middle of them, okay? And remember that protons are surrounded by an electric field. That's the essence of their positiveness. And what happens when two protons try to collide is very similar to what happens when you try to push two magnets together that have the same polarity. If you can see my two little refrigerator magnets here, when I push these two magnets together and I try to push the two north poles together, they kind of deflect and push off to the side. You've probably played with that before. So when the two protons are having a high-speed collision, one will deflect kind of, say, up and to the right, and the other will deflect down and to the left. They almost never come in contact with each other. As the temperature of the star becomes hotter and hotter, the speeds of the protons become faster, and the distance between them at their closest approach, what is called the impact parameter, gets shorter and shorter and shorter. At some point, the two protons get so close to each other, right around 15 million Kelvin, that they can sort of touch one another. And when they touch one another, a new force of nature takes over. Instead of the electromagnetic repulsion, a microscopic force known as the strong force takes over, and it sort of glues the two protons together. You can think of the strong force as being very strong, but very short range, almost like a coating of Velcro on the protons. And the protons can only stick if they get close enough together. However, the only way that you can keep the two protons glued together is if one of the protons undergoes a sort of transmutation, and one of the protons is actually going to have to turn into a neutron. How can you mutate a proton and turn it into a neutron? Well, welcome to the nutty world of nuclear physics. You actually eject the positive charge out of the proton by creating a microscopic little particle of antimatter. It's known as a positron. It has the mass of an electron, but a positive charge instead of a negative charge. Yes, this stuff does exist. Antimatter exists. We've created it inside of particle smashers like the Large Hadron Collider. We also know that it's created inside the interior of the sun. So one of the protons kicks its positive charge out in the form of an antimatter positron. Now, I got a big speech about antimatter that's kind of cool, but I'm afraid if I go down that rabbit hole, we're going to kind of miss the bigger point of today. So let me decide for a moment if I want to do that. The other thing that's going to happen to turn a proton into a neutron is we're going to have to eject a really microscopic yet completely chargeless part. Oh, shoot. That's not what I meant to have happen. A little microscopic particle called a neutrino. And this neutrino is basically a little tiny speck of matter. The symbol for a neutrino is the Greek letter nu, okay? So that kind of curvy looking V is a nu, and it stands for a neutrino. Neutrinos are these microscopic massless, not massless, they're chargeless particles like the neutron, but they have a microscopic little tiny bit of mass, and they're so minuscule in comparison to either a proton or an electron that they can actually fly through the entire sun as if it was transparent glass. If you were to ask me an annoying question like, why do I need the neutrino there? It's because the mass of a neutron is slightly different than the mass of a proton. So the positron kind of takes care of the positive charge, and the neutrino takes care of the little asymmetry in mass between the neutron and the proton. That's one way to look at it, all right? All of this going from here to here is considered step one in the proton-proton chain. Let's write it down together. So instead of writing the proton as a proton, we're going to call it a hydrogen nuclei. A hydrogen nucleus collides and adds to another hydrogen nucleus. It turns into something called a deuteron. And I guess we could put a little positive charge up here for all of these. A deuteron, let's write that down above. A deuteron is the nucleus of a deuterium atom, which is technically still hydrogen. It's one proton and one neutron, all right? It also ejects a positron and a neutrino. Since these symbols are kind of new for you, we're going to label them all. This symbol here is a positron, and this symbol here is a neutrino. What's important in the first step is that you've taken one of your protons and you've transformed it into a neutron. The neutrino leaves the sun and travels into space. The positron, you're not going to like this. The positron collides with an electron, and the two of them annihilate each other and disappear from the universe. Sorry. Okay. Anyways, I don't make this stuff up. They actually turn into gamma rays, but I don't want to get into that right now. Okay. Let's focus on the deuteron because that's a bit more normal. Okay. Now we go on to step 2 of the proton-proton chain. In step 2, the deuteron then smashes into yet another proton, and they turn into a kind of freaky version of helium called helium-3. It also emits a gamma ray, a single short wavelength photon of energy. Now, helium-3 is an unstable nucleus of helium. It has 2 protons, but only 1 neutron. So it's not your normal helium nucleus. This particle is unstable. There's not enough neutrons gluing it together, and it's in danger of disintegrating really quickly unless it bumps into another helium-3 nucleus. That can only happen if steps 1 and 2 take place twice. So imagine that steps 1 and 2 are happening kind of close to each other inside the sun, so that you form 2 helium-3s that happen to be right next to each other. You might think this is unlikely, but the reality is the interior of the star still has so much matter that even if the probability is low, there's still a ton of occurrences per second taking place. The final step is that the 2 helium-3s, so you have helium-3 collide with another helium-3. Basically, 2 of the protons get kicked out, and you make, you make one proper helium-4 nucleus. That's 2 protons and 2 neutrons. And you leave behind 2 hydrogens, 2 protons as leftover byproducts. But the result is that 1, 2, 3, 4 hydrogens come together to make helium and 2 gamma rays. That's the net reaction that you have up here. Are you going to be an expert in nuclear physics now that you've written down the 4 steps of the proton-proton chain? Absolutely not. But it is cool just to get your toes wet to try to think about some of this stuff happening inside the sun so that you understand how nuclear fusion works. Every time you sit on the beach, or if you take a walk today after class and some of that nice, warm, visible sunlight strikes your face, all of that energy started its life somewhere inside the belly of the sun as 2 gamma rays generated during the proton-proton chain. So this is basically where sunlight comes from. This is the sunlight. Sunlight is not in the form of gamma rays because the gamma rays will go through a wild journey from the center of the star to the edge of the star. I just want to give a second here for you guys to catch up to me. You got all that, Kim? Okay. So what happens after the gamma rays are created? I'll explain that, and then we'll move on to talking about planets. Let's imagine you're inside the core of the sun, and you've just generated, oops, let me try this again here, guys. You're inside the core of the sun, and you've just made yourself some very short wavelength gamma rays. And the gamma rays are going to try to wiggle their way out of the sun. The plasma inside the sun is so dense that every microscopic fraction of a second, those photons are crashing into other protons, neutrons, and electrons. So for instance, the gamma ray might start down here inside the core of the sun. But as I'm going to draw crudely here, because that's the best I can do, as the gamma ray tries to wiggle its way out, it will collide with an electron and then a proton. It's basically going to play a big game of pinball as it bounces around, scattering off of other ions and particles in its journey through the sun. This chaotic pinball machine-like journey, where photons scatter off of free plasma particles, is called in mathematics a random walk. It's a random walk because the particles are randomly scattering their way through the interior of the sun. To try to help you visualize the random walk, let's just look at a couple of cartoon pictures here. This is a computer simulation of a 3-dimensional random walk where an imaginary photon is scattering off of electrons and protons millions of times per second. The gamma ray might have started its journey here and ended its journey there. But you can see that it did not travel in a straight purple line from point A to point B. It scattered off of so many particles that it took a chaotic and meandering journey on its way from point A to point B. What might be hard to visualize or understand is that the sun is so big and photons are so small and the number of scatterings so high that a typical photon, one single photon, takes roughly 1 million years to random walk its way from the core of the star up to the surface. 1 million years. That means even if you turned off nuclear fusion in the sun today, the sun would continue to slowly leak light out of its body for the next 1 million years, and you wouldn't even notice it in your own lifetime. The sun is a pretty intensely massive and very large ball of plasma. Another thing that happens during these scatterings is that the photons lose energy with each collision through something called Compton scattering. I think I might just show you an internet picture rather than try to draw it myself. My art skills are not super good. Compton scattering. I don't know if we can find a good picture, but I'll try. So what happens is, here's a kind of groovy picture. Let's see if this looks any good when okay. So don't worry about the math. You don't need to understand that. But what happens is the gamma ray comes in with some wavelength, and it strikes an electron, kind of like a cue ball hitting the 8-ball in a game of pool. The electron picks up some kinetic energy, and it it heats up and drives the electron away from the collision site. The photon ends up losing energy, and as it loses energy through the collision, just like two cars colliding with each other, the energy loss is translated into an increase in wavelength. So I want to make this a little bit cartoony, but the photon that comes in might be a gamma ray, and once it collides with this electron, it scatters to a longer wavelength and it turns from a gamma ray into an X-ray. Then that X-ray will collide with another electron and it will scatter and lose some energy, and it will go from an X-ray into a UV photon. And then the UV photon will scatter into something and it will lose energy. By the time this stuff wiggles its way to the outer layers of the sun, it's been scattered so many times that you basically have a whole black body spectrum of photons, from gamma rays all the way to visible light and even infrared and radio. Also, the convection zone kind of messes things up because energy is transported by blobs, not by light. All I wanted you to know is it's reasonable that what starts off as gamma rays ends up coming out of the photosphere as sunlight, because those photons have a sort of chaotic journey through the star. That's the only message I wanted you to know, all right? By the time you get to the sunlight at the photosphere, it's really basically just like a hot gas that is glowing, just like the hot gas here in this lighter. It's more about temperature than it is about the nuclear energy that originally created this stuff. Energy goes through various mutations on its journey through the sun. In the core, it's created. In the radiation zone, it is scattered. In the convection zone, the energy becomes bubbles of gas. In the photosphere, it is again transformed into light because the light can escape. And that's how photons are generated in the star and eventually make their way to your face on a sunny Monday afternoon like today. Dramatic demonstration of sunlight. Okay. That's all I want to do on the sun with you guys. I hope you enjoyed it. And now we're going to sort of switch gears awkwardly in the middle of our lecture, and we're going to start thinking about the other planets in our solar system. That's sort of the lecture for this week, but we had some bits to finish up here today. Let me erase up. Okay. So today we're going to cover a part of your book called Chapter 7. It's an overview of the solar system. Let's look at a couple different pictures. I actually might want to open up one more slideshow here, just because I like the overview of the solar system that I have here. This is pretty good. Do you guys know the mnemonic device to remember the names of the planets? When Pluto used to be a planet, the mnemonic device would be, "My very educated mother just served us 9 pizzas." Ever since they demoted Pluto to dwarf planet status, people have suggested, "My very educated mother just served us nachos." I don't like this as much because my student from a former class came up with a much better version. "My very educated mother just served us nothing," which I think is much more woke and appropriate for the times. Okay, so "My very educated mother just served us nothing" is going to be my preferred mnemonic device. You guys can pick your own. But it will help you remember the order of the planets in a pinch. There are real bona fide planets. And then there are smaller, weirder things that we don't quite classify as planets. We call them dwarf planets. Most of them are out near the orbits of Pluto, like Eris and Haumea and Makemake, probably weird things you've never heard about before. There is an overgrown asteroid known as Ceres. Ceres is the king of the asteroids and is large enough to deform itself into a sphere, just like a large moon. And Ceres is now also considered dwarf planet status. At some point, I'll show you a picture of Ceres. We only recently, in the last few years, managed to image it properly. But today we'll focus a bit more on the planets and learning some details about them. If you haven't learned this before, we can divide the planets of the solar system into two sort of categories. The inner planets are called the terrestrial planets, or the rocky worlds. The outer planets are called the gas giants, or the Jovian worlds. And they have some striking differences that we'd like to point out. At some point, I'll try to teach you why the solar system formed in this way, with rocky planets close to the sun and gas giants far from the sun. So let's make an overview of our solar system. We have the sun. We have Mercury, Venus, Earth, Mars, okay? Remember that this is Mars and this is Mercury. In between the orbit of Mars and Jupiter, we have an asteroid belt. So that's where the majority of the asteroids in the solar system are. And then we get out to the large gas giants. We have Jupiter, Saturn with its beautiful rings, Uranus has a slightly greenish color, Neptune has a slightly bluish color, and then after Neptune are the regions of the comets. I'm just going to write comets for now to drive that home, but there are different reservoirs of comets. The one that's closest to Neptune is called the Kuiper Belt, and Pluto and Eris and other guys like that, so this is Pluto, they are considered part of a reservoir of comets known as the Kuiper Belt. There is an even bigger reservoir of comets that surrounds the entire solar system in a big shell. And that big shell is known as the Oort cloud. I may not actually get to the Oort cloud and the Kuiper Belt because the class will probably end. That might be my fault for spending too much time on the history and the physics, but I thought that stuff is potentially useful to you in your future. The Oort cloud is a secondary reservoir of comets. Let's see if we can find a more professional well, let me just let you guys catch up to me here. I'm going to start to run out of time here, but you know, we'll get another little tidbit or two in before we have to stop. I have another picture. I really enjoy this picture because you can kind of see sort of the scale of the solar system. I want you to be very careful here, students. In order to get the entire solar system on a single image, we created a logarithmic graph where distances become telescoping as you go further out. Notice, for instance, this is 1 astronomical unit here at Earth, but that by the time you get to Saturn, you're at 10 astronomical units, okay? The Kuiper Belt is inside here between Neptune and roughly 100 AU. This is the edge of the sun's magnetic field. We call the edge of the sun's magnetic field the heliopause. It's kind of like a magnetic bubble that is considered one of the boundaries of our solar system. Notice that the Oort cloud is absolutely huge and can span a range anywhere from 1,000 to 100,000 AU. So that outer reservoir of comets is really massive. Comets that we see on Earth come from one of two areas. They either come from this area, the Kuiper belt, or they come from this area, the Oort cloud. The ones that you have heard of before, like Halley's Comet, are usually from the inner Kuiper belt, and they return back to the sun every 100 years or so. The ones that are from the Oort cloud, you might only see once in a lifetime, and they'll never come back again. In other words, this is the reservoir of short period comets, and this is the reservoir of long period comets. It's different. I just wanted to kind of give you a little overview. For the rest of our class next time, we're going to sort of spend time talking about differences between terrestrial and Jovian planets. And let's see if I have time to do that today. I'm at 1:14, so I'll list some differences between terrestrial and Jovians, and then we'll break a little early and we'll think about how we want to do lab, okay? Okay, so there are two major classifications for planets. And we're just going to list some of the differences so that you're familiar with them. Next time, I'll get into studying the differences. So there are terrestrial planets, sometimes called rocky planets. And then there are Jovian planets. Sometimes called gas giants. They sometimes called terrestrial rocky planets, okay? Terrestrial planets are usually smaller. Jovians are larger. Terrestrial planets, at least in our solar system, are close to the sun. And there's a reason for that. Jovians tend to be far from the sun. Let's talk about more important characteristics, the compositions. Jovian planets are always a mixture, or almost always a mixture of rock and metal. Usually rock on the outside and metal on the inside. Jovians are on the other hand, are hydrogen and helium gas. They literally don't have solid surfaces, with something that today I'm just going to refer to as ices. You can think of it as normal water ice, but there's also other types of ice as well, like ammonia, methane, and even carbon dioxide, okay? We'll get into the chemistry of ices next time. In fact, put a note there, Jenna, because you're almost always in class, and you are too, Kim. If you'll both put a note for me, remind me that I'd like to start off the next class with a description of hydrogen ices. Other things. This is going to be another thing I do next time. Terrestrial planets have high densities. I have not defined density yet, but I'm presuming that you've heard this word before. The typical density of a terrestrial planet is 5 grams per cubic centimeter, something like that. And Jovians, by contrast, have low densities, typically close to that of water, 1 gram per cubic centimeter. Next time, I want to get into the definition of density, and I want to talk about how important that is for the study of planets, more important than you might believe. So once again, if you guys can take another note, next time I want to get into the weeds on that, okay? Here's a question to test your knowledge. How many terrestrial planets do you think have moons?
All of them?
No. Earth has a moon. We know that. Yes, Ryan, 2 of them. Do you know what the other planet is that has moons besides Earth?
Is it Jupiter?
Well, Jupiter's not terrestrial, right? We're just talking about terrestrial.
Okay.
Yes, Ryan. Ryan is correct that Mars is the other planet that has moons. Mars's moons, however, are really small in comparison to ours. They're basically just captured asteroids. That's all they are. So if you think about it, considering that only 2 planets have moons and only Earth's moon is a big moon, it's fair to say that terrestrial planets have few to no moons. On the other hand, all of the Jovians have moons, and some of them are stupid big. Some of the moons are bigger than the planet Mercury. Lots of moons. Another descriptor, no terrestrial planets have rings. And it's going to turn out that not only Saturn, but all of the Jovians have rings. So these are some of the major differences between terrestrial and Jovian planets. I also would like to throw in some magnetic field stuff, but I'll get to that later. This is, for starters, a good way to think about the difference between terrestrial and Jovian planets. Okay, here's what we're going to do. We're going to pause there because that's a good conceptual break. And I also I'm going to need a little break before lab time. It's currently 1:20. I only got 2 people sharing video, but I'm thinking maybe I'll do your lab with you today. You know my rule. I want to have 5 people. So I don't know if anyone else wants to I know Ryan always is participating in his own special way, but I guess we have 1, 2, 3, 4 others. I just never know if these other people are kind of with me or just totally checked out, you know? So I do have a recording of the rotation of the sun that I could drop on you, but I'll see if I can find some tracing paper. And if I can find some tracing paper, then I'm down to do it with you because it doesn't take too long, okay? So I'm assuming, Jenna and Kim, that you'd rather do it live than pre-recorded. That's usually a bit better for you guys? All right. If you don't care, then you're going to make me rethink things. So you have to tell me whether you care or not.
I think it's fine.
I agree with Kim. Yeah.
What's fine?
Doing it live.
Okay.
Exactly.
Michael K is flexible. All right. Let's why don't you guys see if you can fish up some tracing paper or some white paper? Maybe let me see if I can find that tracing paper, but I'm down to do it live because it doesn't take very long, okay? And it's kind of fun. So give me 15 minutes just to chill and drink some iced tea or something and maybe eat a leftover piece of pizza. And then after that, we'll do it. So if it's 1:20-ish, let's say I'll meet you guys back. I need a little extra time today. So 1:40, we'll kick things off, okay? All right. I'll pause the recording until then. Okay, Astronomy 1010. Welcome to Lab 8, where we're going to measure the rotation of the sun by following some sunspots. Let me show you the getup that you would need to really do this lab perfectly. The first thing which everyone should have that I talked about at the beginning of class today is at least 3 pages from your rotation of the sun handout that I provided you on Blackboard. This page shows you the disk of the sun with some sunspots, probably from the TRACE satellite, ironically. And then a couple of real simple analysis pages, which you could either print out or even try to recreate exactly as they appear here, with a space for spot A and some analysis section. So basically, you could recreate these 2 pages if you had to. The other thing that would be really helpful to have is just a simple piece of tracing paper. I cut mine to be about 4 inches on a side, so 4 inches by 4 inches square. or if we want to use metrics, about, 10 centimeters on each side, roughly the length of one good scissor stroke, okay? Tracing paper is going to be really great if you want to track the sunspots. The other three things that we might want to have, a ruler, of course, is always helpful for measuring the sunspot paths. It would be really nice if you had a simple compass or something you could make a circle with. Otherwise, you're going to have very, very good tracing skills. And the last thing that would be very helpful to have is a simple, 50-cent protractor. So a compass and a protractor would be nice. I know that not everyone's going to be able to get these materials together. I'm sure of it. Please just make do with what you can. And as long as it's not too offensive, if you can turn in something that looks like what we did today, I'll consider that acceptable. Okay. Let me make a small adjustment to my camera here. Actually, I'm gonna do this and then I'm gonna do that. Okay, I'm going to use my iPhone today, as always, as a kind of portable and remote camera. That should allow me to sort of show you what I'm doing here. Okay, so the first thing we need to do to get started is we need to make a perfect model of the sun on this tracing paper that matches the suns that we see here on this sheet. So let's talk about how we're going to do that. I'd like us to go into share mode here. Let's see if I can pull that off. Share screen to my iPhone. Okay, everything looks pretty smooth. Just a moment while it connects. All right, I'm going to use this roll of tape here to kind of balance my iPhone. Okay, so let's just go to one of our suns, say the first one. And let's start by measuring its diameter in millimeters. One of the things we always try to do when we measure the diameter of a star or planet, always try to measure them from North Pole to South Pole, because planets and stars tend to bulge a bit at their equators. What would you guys say is the height of this sun in millimeters?
About 54 millimeters.
Good. And that means the radius should be half of that, right? So the diameter is 54 millimeters. We want to set our compass to the radius. 54 divided by 2 is 27 millimeters. Let me show you how we're going to do that, okay? We're going to go to the back of this page where it's just blank. In just any old place, it doesn't really matter where. Let's make a line that is 27 millimeters long. And we're going to be, oh, I need my pencil here. All right. I'm going to sharpen this up. Sharp pencils are going to be the way to go here. And I'm going to go through great pains to make a line that's exactly 27. That's 27 right there. I usually like to make a little tick at 27 and a tick at 0. That's how I do it. Those ticks will be helpful. Then I can be sure that I've gone 27 and no further. That's what my 27 millimeter line looks like. And of course, I'm going to set the radius of my compass to that. I'm going to put the pokey, pointy part at 1 tick mark. And I'm going to adjust this set screw that you see here right in the middle with my fingers until this guy is right at the other tick mark. And I'm even going to kind of test it out. Make sure that it hits right on the line. Okay, there I go. What I'm going to do next is I'm going to put my tracing paper down. I'm going to poke it. I'm going to rotate, spin and pin it and spin it nice and carefully to make a nice, perfect model of the sun that hopefully will match. Notice, ooh, try to avoid that stuff. Let me clean that up. Okay. So now the moment of truth, what we're going to do is we're going to compare it to my first sun and see how they match up. If they don't match up, you did something wrong and you're going to want to do it again. Hopefully I've got enough experience where this came out correct. Yeah. You can see that my traced circle matches up pretty damn good with the model of the sun. So I measured correctly and I did all that good. What I'm going to do now is I'm going to trace over the registration tick marks. Believe it or not, it's really easy to sort of rotate or drift your tracing paper. So putting in your north, south, east, and west registration tick marks are a really good idea. I'm going to label this top one at the top north. And east is actually on the right here. It originally would have been up backwards, but I think they flipped it for us. Okay, let's talk about the spots that we're going to track. There's the first 6 days and the second 6 days, and we're going to try to find one spot in the southern hemisphere and then a spot in the northern hemisphere. And what I'd like to do is track that kind of darkest spot that you see going across. We're not going to track all the spots. We're just going to try to track one in the upper hemisphere and one in the lower hemisphere. Let me adjust this. Okay. So I believe oh, wow, guys. I'm upside down right now. That's one of my issues. Okay. So I'm not going to track anything on 725. The first spot that I'm going to track is on 727, and it's actually this spot that appears right there in the corner. And I'm putting just a big loose circle around it so I know, so everyone knows which spot I plan on tracking. Notice that my circle is kind of large so that it won't affect my tracing paper. I'm just going to track this one here. It goes to that date on 8-1. Basically, I'm picking the darkest one that I could find, and I'm trying to track it across the southern part of the hemisphere. So this spot, this spot, this spot, this spot, and this spot. Now in the lower hemisphere here, or sorry, now I'm going to try to pick one starting 8-8 that appears in the upper hemisphere. And I kind of can see this really dark spot here. That's the one that I want to track. So it looks like the dark spot starts there on the first day on 8-8. Then on 8-10, it'll be this dark spot there. 8-12 here. 8-14, it's going to be here. 8-16 there. And 8-18, it's almost up the page. So let me just show you the spots that we're planning on tracking. The first spot, the lower hemisphere, has 1, 2, 3, 4, 5 observations. The second spot in the upper hemisphere has 1, 2, 3, 4, 5, 6. Let me just kind of leave that frozen there for a second so that anyone who got lost in the sauce can sort of examine this and find it later. All right, let's track our spots. So each time I track a spot, I'm going to be careful to match my registration tick marks very carefully. Okay. So what I'm going to do is I'm going to sort of line up my circle, make sure all 4 tick marks are as good as possible. And then what I'm going to do is I'm going to fill and color in the dot. And underneath that dot, I'm going to put the month/day, 7/27, in some easy to find location. So 7/27 in really small font, I'm putting underneath it. Let's go over to our next spot. I had a lot of coffee this morning and a lot of iced tea during lecture, so I'm a little caffeine jittery right now. So please forgive me if that comes across in my procedure here. I didn't get to eat during my little tea break. I got distracted. All right, I'm going to track this spot next. Put a dot there. And this spot is at 7-30. So I'm going to 7-30. Now we'll go over to my next sun. All right, 8-1. I'm gonna mark my registration tick marks. That's 8-3. This is a classic lab, by the way. It's really cool when you can do it with the actual sun projected using a heliostat, but I don't have one of those set up in my house, so. And this is 8-6. I'll put that over here on the side. All right, now let's track our upper spot. Match my registration tick marks as close as I can. I think this time I'm going to track the spot and then put the date. Well, no, I'll do it one at a time. 8-8. 8-8. Let's go over to 8-10. Okay. That's 8-10. That's 8-12. You have to have really tiny handwriting to do this right. 8-14. I'll go to 8-16. And lastly, 8-18, right on the edge there. Okay. So I've now finished. And what I have sort of looks like this. Just going to give you guys a second to kind of catch up to me. All right. What we need to do now is we need to make a best fit line through the sunspot in the northern hemisphere. I'm going to call that the A spot. The one in the southern hemisphere, I'm going to call that B spot, just for reference. I want to make a best fit line through each of the spots. You can see that they kind of drift and curve a little bit, but I want to make a best fit line that is as horizontal as possible. That means kind of equal numbers above and below. I'm going to try to hit this right. I'm not sure I did it perfectly, but it's pretty close. So you can see a horizontal line there. I might have a few too many below than above, but I'll try to get the next one a little better. I'm forcing that line to be horizontal. Okay. And what I'm going to want to do is measure the length of these two lines. Let's start with the A line. The length of the A line on my measurement scale here, I don't know if you can see this. It's about 50, fudge. Sorry, the phone popped out. Okay, so it would have been really helpful to have been born with 3 hands for this job here, but the length of my A spot, the upper one, is about 50, sorry, you're not seeing this right, is about 52 millimeters. You can see it's about 52 millimeters across. So what I'm going to do is I'm going to go to my first analysis page. And here you're going to have to follow my instructions really carefully. I'm going to make a line that's exactly the same length as the line of my A spot. And I'm going to put it right here, right next to the A spot, okay? So I'm going to make a line starting right near A, and I'm going to make it exactly 52 millimeters long. So make a tick mark at 0, tick mark at 52. I'm also going to find the midpoint of the line. If half of 50 is 25, half of 52 should be 26. So I'm going to make a vertical cross right at 26. I don't want to confuse that with a spot later, so I'm going to kind of make it in the middle. And let's talk about what we're doing here. In this page, I can see the sunspot rotating across the front of the sun. But once the sunspot disappears over here, I'm going to lose track of it, and I'm not sure when it's going to come around again. Instead, what I'm going to try to do is I'm going to make a top-down bird's eye view of the sun, where I imagine cutting through the sun at this latitude, and I'm going to watch the sunspot rotate across the belly of the sun. To do this, I'm going to need to make a sort of model of a top-down view of the sun. So this is 52 and 26. Let's set our compass equal to this radius. Does that look right to me? Something looks funny, but it could just be that I'm hungry. Yep, it's about right. Okay. So I'll poke at the top there. I'm going to adjust my radius a tiny bit. And I'm going to draw in a hemisphere, okay? This is a top-down view of the sun, and what I'm going to try to do is I'm going to try to project the sunspots onto this line at their exact positions. To do this, it would be really helpful to have some squishy paper to put underneath. I've got a sort of yellow legal notebook pad here. Helps to have a good working surface when you do these labs. Okay, so check out this maneuver. I'm going to place my A spots, the tracing paper, right over the line. And in order to get the spots at their exact location, I'm going to poke through using the pointy part of my compass like this. Dink. I'm going to try to force the spots to be right on the line. Dink. 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 Okay. And now, if I lift them up, I can see the little divots and I can color them in. And that's exactly where the spots should be on the side latitude of the sun. I'm going to put the dates underneath each spot as well. 8/8. 8/10. 8/12. 8/14. Helps to have really tiny handwriting here. 8/16. And 8/18. What I'm going to do is I'm going to track 2 of the sunspots. Well, let me just give you a second to catch up. Let me get some water while you do that. I'm actually so hungry and over caffeinated that I feel a little dizzy right now. So hopefully I won't die during the recording of this lecture here or perish right in front of you. Okay. All right, so let me show you how we're going to do this. We're going to project two sunspots up onto the surface of the sun so we can measure the angle through which the sunspot rotates. I don't want to pick them too close to the center or too close to the edge. So I'm going to focus on these guys here at 810 and 816. And I want you to watch how I do this. I'm going to vertically project them up to the surface of the sun, but I will not go past the surface of the sun. So I'll make a horizontal line there, and I'm going to make a horizontal line there. All right? The next thing I'm going to do is I'm going to draw a line that goes from the center through the intersection of where the spot hits the surface of the sun. And this line I'm going to extend out as absolutely far as it will go because I'm going to want to measure it. So what I'm going to do is I'm going to extend it way the hell out. Notice that it goes from the center to where the spot intersects the surface, and then it keeps going. Do the same thing for the other side. From the center to the intersection with the surface and then beyond. Now I'm going to do the whole damn thing that I just did for the A spot. I'm going to do that for my B spot. And here I'm going to move kind of quickly, so you might want to try to either catch up or just, I don't want to go too slow because it'll make the recording really tedious. First, I'm going to measure the length of the B spot line. The length I get for this one is 50 millimeters. So I'll make a line 50 millimeters down here. Oops, sorry, you guys can't. Here, let's bring this up. 50 millimeters will go right next to my B spot, just like I did for the A spot. Tick marks. Make a line. I'm going to mark the midpoint at 25 with a vertical cross. Okay. Set my compass to this, and I'll draw in another hemisphere. Here I've got to adjust my radius by a couple of millimeters. You'll have to forgive me, I'm kind of quick at this because I've been doing it for so long. Now I'm going to track my spots right onto the line. Dink, 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 dink. Okay, so I'll shade in the spots. Notice that I forced them to go right on the line. I'll then put in my dates. 7/27, 7/30, 8/1, 8/3, and 8/6. I'm also going to track two of my spots up to the surface. It looks like the best ones to choose are 7/30 and 8/3. You could choose other ones if you wanted to, but those are probably the easiest. I track them up to the surface, and now I'm going to make lines once again that go from the midpoint through the intersection with the spot on the surface, and I'm going to extend it all the way out as far as the eye can see. Whoop, something like that. So this is where we're at so far. Kim and Jenna, where are you guys at right now? And you're following along with me.
I just finished drawing the long line on the second on spot B, so I'm all set.
Wow, Jenna, I'm impressed. How about you, Kim?
I'm all set too.
All right. I like you guys. You're on top of it. We don't have much more to do. Just bear with me. I'm going to get rid of this pad. Make it a little easier to see everything. Okay. Let's look at what we did up here. I projected 2 spots, and imagine you're watching this spot rotate around the surface of the sun. It starts here on 810 and goes doot, 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 doot over to there on 816. Our goal is to find something called the angular velocity. How many degrees per day does the sunspot rotate? The idea goes something like this. If I were to draw a circle of the sun, hold on. Think about ratios. If my spot starts here and it rotates all the way around the sun, it will go 360 degrees in a full period of the sun, right? On the other hand,
see.
if my spot rotates through some angle theta, it'll go through some angle theta in some unknown number of days. The idea is that the ratio of these things should be the same, that 360 degrees to the period should be equal to the angle rotated by the number of days. I know 360, I can measure the angle, measure the days, and I can solve for the period using algebra. Flip period up, and the period will be 360 degrees divided by the angular velocity. The angular velocity is this. It's the number of degrees per day. So I'm going to measure the degrees the spot rotates, and I'm going to measure the days. This here, theta with a dot over it, means angular velocity, and it's measured as some number of degrees per day. All right, let's learn how to measure the angle that the spot has rotated through. I take my protractor, sorry about the glare, I'm going to put the hole right over the vertex of the angle. That's where the angle kind of meets in an elbow. And then I'm going to pin with my pencil, and I'm going to, watch this now, let me focus it. I'm going to spin and rotate until the 0 degree line perfectly lines up with one of my arms, and I'm going to pin it down. Clearly the angle is less than 90 degrees. So what would you say the measurement of my angle is here?
73.
Good. Let's write that down inside the elbow. We got about 73 degrees there. Let's also, while we're at it, measure the second one. So once again, I'm going to put this at the hole of the triangle. I'm going to pin it and spin it until 0 degrees matches one of my arms. And what would you say is the measurement for this guy?
54?
Yeah, I agree. If you make a small adjustment, it's about 54. Okay, now let's work on the number of days. How many days was it from 810 to 816?
6 days.
Okay, so the time interval is 6 days, and the angular velocity is 73 degrees divided by 6 days. So I have 73 degrees over 6 days. And how many, let's keep 3 sig figs for now to avoid any rounding errors. 73 divided by 6 is 12.2 degrees per day. Notice how I write my units, degrees/day. Okay, this one might be a little more confusing. This is July, right? How many days do we have in July?
31.
So how many days is it to go from July 30th to July, June, July, to August 3rd?
5.
Hold on, we got to be careful here.
Wait. Oh,
30
6. Sorry.
No. Watch, slow down for a sec. 30 to 31 is 1 day. 31 to 1 is 2 days. 1 to 2 is 3 days. And 2 to 3 is 4 days, right? 1, 2, 3, 4. Do you see how I was kind of hopping through the days there, Kim? Did you follow me?
Yeah, I was counting the 30th as the first day. That's fine.
So you have to be careful because 30 to 31 is the first day, right?
Mhm. Yep.
Okay. Okay, so we just learned something there. So we have 4-day interval and 54 degrees divided by 4 days is 13.5 degrees per day. Now, they had in mind that we would choose a third spot as well, but I think 2 spots is fine for the purposes of this exercise. So we're not going to do a spot C. What we do need to do is calculate the average angular velocity. We do that by taking the average of 12.2 and 13.5. So let's do that next. 13.5 plus 12.2 is equal to 25.7. Divided by 2 is, let's say, 12.9 degrees per day. Now we're going to apply the mathematical rule that we learned before. The period should be based on our corresponding ratios. If you followed my logic there, the period should be 360 degrees divided by the average angular velocity. So we'll do 360 and we'll divide it by 12.9 degrees per day. So let's just write that out over here. This is going to be the so-called synodic period. The synodic period will be 360 degrees over 12.9 degrees per day. And I get 27.9. What should my units be? If I divide degrees by degrees per day, what will my units be?
Days. Oh,
Yes, you're correct. Degrees cancel with degrees. 1 over 1 over days is days. So 27.9 days. This is not the final period. This is the so-called synodic period. Let's think about why. During the time that we measured these sunspots, say from here to here, if you think about it, class, the Earth was actually in motion during the course of those 2 observations. We saw the sunspot when it was over here. We tracked it to over here, but the Earth was also spinning around the sun during that time. What we want to do is subtract out the spin of Earth and find the rotation of the sun relative to the fixed background stars. That turns out to have the same relationship that the synodic and sidereal periods of planets do from an earlier point in this lecture. It's going to turn out here the best version of the formula, considering the sunspot is kind of like an inner planet, is that the sidereal period can be computed as 365.25 days times the synodic over 365.25 days plus the synodic in parentheses, okay? All right, so let's type that in. 365.25 times 27.9 divided by, open parentheses, 365.25 plus 27.9, close parentheses, equals. And my answer comes out to 25.9, which I'm going to round back to 26 days. I'm only keeping 2 sig figs at the end because my degree measurements only had 2 sig figs. And thus we've computed the angular velocity of the sun is 26 days. I've done better before. The true answer is 25 days, but that's not too bad for a little crappy student lab where we just track some sunspots on a tracing paper. And this is what you will turn into me for the final product. You will turn in a scan of your tracing paper if you did that, a scan of this page, and a scan of that page. Okay. Let me say, guys, that I've been a little bit behind on the grading. I know you've noticed that. I caught up a little bit last night, but I'm still not finished. Please bear with me, and I will try to get to that maybe even today. All right. Once again, this is the third page, second page, and if you were able to follow along with some kind of a tracing paper, it'd be cool to see that. If you weren't able to do this, fine, I'll deal, okay? But you better at least give me these 2 pages. Okay, I hope you enjoyed learning how to calculate the rotation rate of the sun. Good Monday, Hangs, and I'll see you guys on Wednesday. We'll learn more about the solar system. We'll learn how to calculate densities, and we'll do a homework problem on the overview of the solar system. Okay? Okay. Live
Thanks.
long-
Have a good.
Yep. See you, Jenna. See you, Kim. See you, all the background people. Take care and bye. Bye, Ryan.